Hello and welcome back. This is Logan and today we're going to be delving into the world of analog functions on the TiVo Launchpad. This is the third video of our series for Microcomputer Engineering from the University of British Columbia's Okanagan campus. If you have yet to complete the first two labs, please refer to the previous videos for instruction. As always, if you are looking for my or Dr. Eldengar's contact information, look on Canvas. In addition, you will also find the lab open office hours posted on Canvas as well. To complete today's lab, you must have access to inertia and a TiVo Launchpad, as well as a potentiometer, breadboard, piezoelectric buzzer, and jumper wires. As we will be working directly with hardware today, it is important to follow the safety guidelines. Always make sure to power off your circuit and board before modifying it. This will make sure you do not accidentally short anything. Handle components gently and always grab printed circuit boards by their edges. Finally, be confident in your work and double check that your circuits match what is described in the lab manual. The first thing we must do today is connect a potentiometer to our Launchpad. This is relatively straightforward and I'll go through it myself for demonstration. The first thing you should do before modifying your circuit is make sure it is not powered. It seems like a simple thing but can sometimes be forgotten. Just the other day, someone I know accidentally cut a wire while it was still powered and blew a fuse on a control board. It happens and we are not using a very large voltage, but if you can get into the habit of double checking, you'll be far safer. To get started, connect your potentiometer to the breadboard along 3 separate rows. Just like that. Make sure it's perpendicular to the power rails, and this will make sure that none of the pins are connected. You'll find that the holes of a row in a breadboard are connected, while each row is isolated from the others. A potentiometer like this has 3 separate pins. 1 for the signal wire, which is in the middle, and 2 for power and ground on either side. Depending on which you choose, the signal will increase in either a clockwise or anti-clockwise direction, and you'll have to decide which one you want to do. Next, you'll also have to decide which pin you connect to on the TiVo Launchpad. I'm going to be using PB4 today, which is connected here, and connect my wire to the middle, just like that. Next, you'll have to connect to power, which in this case will be using 3.3 volts. Just connect to 3.3 on one side, and then to either side of the potentiometer. And finally, we have to connect to ground, and there are a couple ground pins to choose from. I'm going to connect to mine here on the top right of the board, and that's all I need to do. My potentiometer is officially hooked up. Today we'll be using analog functions, such as analog read, which translate an analog signal on one of the microcontroller pins to a digital one through the analog to digital converter, or ADC. An ADC is an integrated circuit that samples an incoming analog signal and converts it to a ratiometric digital representation. A ratiometric signal is one that has a set minimum and maximum level, and any voltage between that is simply a ratio between these, the resolution of the converter, and the respective voltage. Different ADCs have different resolutions, and in the case of the TiVo Launchpad, the resolution is 2 to the 12 bits, or 4096. Any voltage between 0 and 5 volts will therefore be a ratio between 0 and 4096. There is obviously some loss of data in this conversion, but for most applications this is sufficient. If you ever encounter a situation where you need a more accurate reading, there are more advanced ADCs that you can use. Now that we've described how an analog signal is converted to a digital one on the Launchpad, what about the opposite? In inertia, we would use the function analog right to accomplish this. As you may have guessed, however, there is no way for the Launchpad to generate a true analog signal. One way to approximate one is through the use of pulse width modulation, or PWM. A PWM signal is a square wave with a fixed period or frequency. By changing how long the signal is on during that period, this is the duty cycle, we can change the average voltage that is sent and is subsequently received by another device. To a human observer, this is typically enough to approximate an analog signal, as the PWM frequency is quite high. We can then fade LEDs or modulate audio signals following this method. It is also possible to get an even closer approximation of an analog signal through the use of a capacitor, but we will not be doing that today. PWM signals are used everywhere in embedded systems, from dimming LEDs to sending control signals to actuators in a robotic arm. The last thing you'll need to know about today is a piezoelectric buzzer. A piezoelectric buzzer is made of a simple membrane that is oscillated using the electric signal and a piezoelectric material that converts electric charge to mechanical motion. By sending an oscillating signal with a high enough frequency, we can create tones through the buzzer. The circuit setup is very simple, as all you need to do is connect one side to ground and the other to your output pin. One potentially tricky part, however, is to make sure that you connect the positive side to the longer pin and ground to the shorter pin. If you don't do this, the buzzer likely won't work correctly. With that done, it's now time for you to complete the lab yourself. If you are successful, you should be able to read an analog signal from the potentiometer and play a simple melody with the buzzer. As before, record a video of your final working product and upload it along with the lab report and your main.ino file to Canvas. Have a great week and catch you in the next one.